Hello, and thank you for joining us today. It is 11 a.m., so we will get started. I am Lori Lehner, the Global Training Manager for the Mobile Solutions Aftermarket Group at Donaldson Company. My team runs the Donaldson Training Academy, among other forms of training. In today's webinar, Matt will cover how contaminated fuel impacts your equipment, changes in engine systems, today's fuel, how fuel cleanliness is measured, and how to ensure your fuel meets the requirements for today's engines. This educational webinar may fulfill CE credits. You will receive an email after the event to request a certificate of completion. For those unfamiliar with Donaldson Company, we are a filtration and separation company that's been solving complex filtration challenges for over 100 years and continues to advance filtration for a cleaner world. Today, we are one of the largest providers of unique filtration technologies, and we excel at producing high-quality filters and parts. We pride ourselves as having a global reach with a local touch. Our world headquarters is in Bloomington, Minnesota, and we have 55 manufacturing plants and 11 distribution centers around the world to support our customers. Before I introduce Matt, I would like to quickly explain how to engage during the webinar. As you think of questions, please type them in the chat box and Matt will answer them at the end of the webinar. During the webinar, you can respond to quick questions or give your reactions by clicking on the face icon at the bottom of the screen. There will also be 2 Slido interactive questions you can access by phone or the Slido panel that opens on your WebEx screen. Now I have the pleasure of introducing our speaker today. Matt Graham has over 10 years of experience in hydraulic and bulk fluid applications. Working with major outfits throughout the U.S. and Canada, he assesses filtration quality and develops innovative solutions to protect Donaldson customers' bottom line. His work ensures that heavy operating equipment meets specification and quality filtration requirements, ultimately optimizing systems, improving performance, and extending equipment life expectancy. Now, to better understand today's audience, we'd like to know how familiar you are with bulk fuel filtration. To participate in this survey, you may either answer in the Slido panel if it is visible on the right side of your screen, or you may scan the QR code with your phone. If you scan the QR code, it will ask you for the password, which is filter, F-I-L-T-E-R. It looks like we have a range of knowledge in our audience today. Thank you very much for completing this survey. And now I have the pleasure to pass it over to today's presenter, Matt Graham.
Thanks, Lori. Much appreciated. Thanks, everybody, for taking the time to hop on today's webinar. We'll jump right into it. First off, kind of answering the question, why do we filter bulk fuel, and what's the really reasoning behind it? Well, first, especially in the mining and oil and gas environments, heavy equipment environments like that, our working environment brings with a lot of contaminants to that space. Number one is the dust and dirt. Airborne dust particles move all around the site, and every time that we actually dispense fuel into something, we have to replace that volume of fuel with sucking it back into the breather. Anything that's floating around in that atmosphere is going to be pulled into there. Dust and dirt are likely culprits that get sucked right into that tank. Along with any moisture, we don't think about that nearly as much. A lot of tanks maybe have rain covers or caps. But any humidity or moisture that's in the air, or even water from production of whatever the environment is, that moisture gets pulled back into that tank too. Think about, especially in the summer or spring and fall days, very humid outside. That humid air gets pulled into the tank and is able to come in contact with any of that fuel. Now, that working environment, those contaminants that are there, do lead to some effects that are on equipment. When we think about lubricants, probably everybody's fairly familiar with that. If we have contamination in the lubricant circuit, we have the decreased component life. It might come up with unplanned maintenance, maybe some fluid contamination, and overall increased cost for that system. But a lot of times we don't transfer those same thoughts to the fuel circuit, when in reality, those same issues occur on the fuel side of it, but we don't necessarily always think about keeping our fuel up to that same level of cleanliness. We can see frequent injector or pump replacements. We might see onboard fuel filter replacements have happen at a high degree, maybe large contaminants or sludge like you see on the picture there. Or even if there's biodiesel being used, we might see microbial growth or glycerin dropout, some of the different things that can occur if we allow that contamination into that fuel system. Now, one of the questions that gets asked quite a bit is, why the big change? Why are we talking about this now? I've been doing this for, 20, 30 years, sentiments like that of, we've been having filtration the same way. Why are we changing it? Well, the diesel engine itself at its core is relatively the same, but what's changed dramatically is actually how we deliver fuel to those cylinders. So if you guys have been around long enough, you've heard, different changes with the EPA and being able to get higher efficiency for that fuel out of that engine. And really the best way in order to be able to do that was to increase the fuel injection pressure of those systems. So if you're familiar with the term high pressure common rail, almost all diesel engines have now changed over to that system. And where we used to have injection pressures of 3 to say 5,000, maybe 6,000 PSI, we're now living in a world where injection pressures are 40,000 PSI plus. We've also at the same time reduced sulfur. We've added biodiesel to systems. We added exhaust after treatments. We've changed the oil viscosity levels and definitely added a lot of computers and overall cost to these engines. That makes a big difference in how we are able to operate them. Those tighter tolerances no longer can deal with that same level of fuel quality that we previously had. If you're familiar with some of those older series engines, you might recognize those filters typically were 10, maybe 30 micron for on-engine fuel filters. Today's engine fuel filters set usually somewhere between 2 and 6 microns, because that is the size of particulate that is damaging to those injectors and to those pumps. Somewhere in between bacteria and red blood cells, or 2 to 5 microns, those are the size particles that are damaging to those components within that fuel system. Now, another question that gets brought up quite a bit is, okay, engines have changed, how we deliver fuel to them has changed. Well, I would assume that also then that the fuel has changed. And you're right, there are specifications. I don't expect anybody to actually read and look at this in small print, but there are specifications for how fuel is regulated and what it needs to hit. The unfortunate thing, although we've changed bio content, so we have certain allowable bio contents within diesel fuel, we've reduced the sulfur content within fuel. The interesting thing is the allowable amount of water and the allowable amount of dirt within diesel fuel has not changed at all since the late 70s. And the unfortunate thing there is today's engines cannot handle that same amount of dirt that was in yesterday's fuel, but still we're allowing that same amount of dirt to be there. And what that means from a testing standpoint, again, I kind of grew up on, doing some farm and construction type stuff. If ever we thought we had a fuel problem, Typically what we do is you dispense it in some kind of clear container, you hold it up to the light and say, okay, does that look clean and dry? Everybody taking a look at these fuel samples here, one's on-road, one's off-road. But if you looked at them, you'd probably say, okay, yeah, that's contaminated fuel. It's not very clear, it's not very bright. You can actually kind of see some floaters in there moving around, right? So, all right, yeah, bad fuel. But when we look at these fuel samples, hold those up to the light, those things look crystal clear. And to the naked eye, looking through it, I don't see any water in there, I don't see any particulate in there. And that test for previous series engines actually worked out pretty well, because anything that you could see in there was, okay, yeah, bad fuel, and that's going to be too big to go through that fuel system. But remember that 2 to 5 micron level that we're concerned with today for today's high-pressure common rail engines, that unfortunately is invisible to the naked eye. So if you kind of look at this chart here, what you can see with your naked eye is about 40 microns, give or take. So yes, if you can see particulate floating around in a fuel sample, it's bad, right? That fuel is contaminated to a level that's not burnable in today's engine. But even if it looks clear and if it looks dry to the naked eye, the unfortunate thing is there's going to be a really high concentration of those small particles within that fuel sample that is making its way into that fuel system and causing damages, but it's invisible to your eye. So how do we tell whether or not a fuel is clean enough or too dirty to be able to be used in today's engine? The answer for that is the ISO cleanliness code. Some of you may be familiar with this. This gets used to measure all sorts of different fluids, whether it's engine oils, hydraulic oils, gear oils, fuel. Essentially what it is a way to describe what the dirt or particle concentration is within a volume of fluid. And you typically are going to see broken up into 3 numbers. One, the first part number, or the first number there, is for all particles 4 microns and larger. The second one is for all particles 6 micron and larger. And then the last one is for all particles 14 microns and larger. When we're talking about fuel and high pressure applications, we have really small tolerances. So typically what we're focused on is that first number in that ISO cleanliness code. So if you hear me for the rest of this refer to a certain number, I'm referring to that first number, which is all particles 4 microns and larger. But the other thing to make sure that we're aware of is that this is not just a linear scale. Each time you actually go up a code, you double the amount of dirt. So it's exponential in the way that it can actually get out of hand really fast. So if we look at that example code there, a 21, we look at the blue line on that chart, there's roughly between 1 million and 2 million particles in that sample if it was given the cleanliness code of a 21. And when we talk about sample size, that's per 100 milliliters. So a little sample bottle is going to have somewhere between 1 million and 2 million particles in there. Now let's bring that back to what that means in the world of fuel. So your average typical diesel storage tank lives somewhere right around a 22. And what you're seeing there on an image is actually that fuel sample ran through a patch test and looked underneath a microscope at about 400x zoom. So typically things are invisible to the naked eye, but what can we actually see with that microscope? So again, very high particle counts, but that's pretty average for what's inside of a tank. I've taken thousands and thousands of samples all over North America, and that's pretty steady of what the average sample is. The unfortunate part is for today's high pressure common rail engines, we need a fuel that is much, much cleaner. An example of what that looks like under a microscope is here at that 12. There's roughly about 2 particles in that entire patch that can be visibly seen. So we have a jump that we need to get from inside that tank at a 22 roughly, or between 2 million and 4 million particles. And before that fuel can be burned correctly in that engine, we need to get down to a 12, or between 2 and 4,000 particles. That's about 1,000 times cleaner than your average tank levels, and that is a lot to be expected of that onboard engine fuel filter. So then we look at that actual injector itself, probably the most susceptible piece within that fuel system that can be damaged or not be able to get to its actual lifeline. So this data here is actually from the largest injector manufacturer in the world. And what they state is that if you're able to get to that 12 level, represented by that green line there, essentially 2,000 to 4,000 particles in that sample bottle, they'll get to what they call their lifetime, or roughly 20,000 hour service interval. But take a look at the lines underneath that. If we even just go up one code, going from a 12 to a 13, we've had more than half the life of that injector. If we go up another code, we're less than a quarter of what that original injector life would maintain. So if you have been a part of any kind of organization or operation where injector life has been extremely diminished, or there's sentiments that, yep, today's engines and their injectors just don't last as long as their previous counterparts, most of the time that is realistically being a result of fuel that is too contaminated to be able to operate in today's high pressure common rail engines. But how does that damage actually occur? Well, here's a side cut view of a typical injector. But that popping valve there, any contaminant that's there that's clicking back and forth is going to round out that hole, and that's that image that you see blown up there in the lower portion of the screen. If you've ever heard the term injector leak down, leaky injectors, or even had extended cranks during start where you get a lot of smoke coming out the tailpipe right at initial startup, typically that's caused from that not being able to hold back that pressure because of those contaminants. And then if we move down that red line all the way down to the injector tip, you see that small little orifice. And that small little orifice is what is atomizing that fuel in order to be able for that fuel to be burned correctly in a high pressure common rail engine. If any contaminants or debris makes it through there, remember we're at injection pressures 30 to 40,000 PSI. If that contaminant makes its way through, those are those same pressures that a water jet cutting machine uses to actually cut through steel. So if you accidentally have any of those contaminants in there, it's going to open up that hole on an injector nozzle tip. And kind of what that ends, some of these pieces look like under a microscope, is when we see those to the naked eye, again, look pretty much like a polished surface. When you look under that microscope at that really small level, we can see those small little nicks. And those are the things that cause those injectors to not be nearly as efficient at being able to atomize that fuel as they previously have. And if a visual of what that looks like, your new injector really gets a nice fine mist. I use the analogy a lot of kind of like putting your thumb over a garden hose. You can get a really nice fine spray. But as you open up that port, or that nozzle at the end of there by allowing contaminants to come through, much like taking your thumb and moving it off the garden hose a bit, you start to get back into a stream in large droplets. That fuel can't be as combust nearly as easy, and it doesn't completely fully burn. What then happens there is you have unburnt fuel that ends up in the exhaust stream. And if you have a piece of equipment that goes into multiple regens or is regenning quite frequently, you're plugging DPFs, you may get check engine lights, you might get reduced horsepower, or your overall horsepower utilization has dropped dramatically. That likely is an effect of that injector not being able to properly spray at that same level as what it once did.
We have another survey question for you. This time, I would like you to scan the QR code with your phone and then enter the word filter, F-I-L-T-E-R. The question is, how often do you experience fuel-related downtime? It looks like the majority of the audience is between monthly and yearly, with the worst case scenario being that some of you even see it weekly.
Thanks, Lori. Well, with that in mind, you probably are curious about some different ways of what we can do to be able to keep these issues at bay. What we've talked about so far is kind of at the whole, a lot of our testing standards that we've maybe historically used to be able to see if fuel is appropriate to be utilized in today's engines is probably not adequate. And we probably all don't have enough time in our day or the resources to be able to test every sample of fuel and send it out to a lab or pull and do patch tests like you saw some of those examples there. So what can we do in order to ensure that the fuel that we're dispensing into our equipment is clean enough for today's high pressure common rail engine? What that looks like is incorporating bulk filtration. We need high efficiency filtration to be able to ensure that in a single pass, we're able to get to those target cleanliness levels before they're put in today's equipment. And there's really kind of 3 steps that can ensure to make sure that that fuel is protected at a high enough level. And we usually go by the terms clean, protect, polish. We want to clean that fuel on its way into that tank, ensuring that any contaminants that are brought to us are removed before it goes into the tank. We want to protect that fuel while it's in storage by having a breather on there. And then we want to polish that fuel on the way out, making sure that no matter what, any fuel dispensed into your equipment is going to be clean and dry and ready for use. I get a lot of questions very often about, well, why would I want to filter it on the inlet as well as the outlet side? It seems like it's kind of redundant. In a sense, it is. But when we think about those standards that I showed at the beginning and what the allowable amount of contaminants and water and different things that can be within a load of fuel, this is what those work out to be. So your typical fuel trailer delivery is somewhere between, say, 7,000 to 10,000 gallons, with most of them hanging around like 7,500 gallons. But within that trailer load of fuel, you can have up to 375 gallons of biodiesel. You can have 1 gallon to 3 gallons of water actually delivered to you. You can have a gallon of glycerin, which is a byproduct of making biodiesel, that even if you buy B0 non-biodiesel fuel, you still have roughly up to about 5% of biodiesel in that, whether you want it or not. We have typically somewhere around 5 or so gallons of additives. That is kind of an unregulated frame. It can be all over the place. And then last but not least, but on average, you're accepting about a cup of dirt for every trailer load of fuel that you go in. Especially in environments like yourselves with mining, oil and gas applications, we're not just going through a trailer load of fuel once a month. We're potentially doing that daily or multiple loads a day. That dirt really starts to add up. The other possibility is, I'm sure everybody's heard about receiving a bad load of fuel, or somebody's bought fuel seconds to try to save some money. A lot of the times that fuel is really contaminated. If that fuel gets put into your tank, once that's in your tank, you own it, it's yours, it's your problem. If we have filtration on the inlet side, those filters are going to be able to remove, capture that contaminant, and stop from any of that from entering the actual tank. Second step in the bulk filtration side is a breather. So most tanks that I've ever seen out there will have a stick breather that might have kind of like a gooseneck or candy cane neck to be able to prevent moisture from raining directly into that tank. They might kind of have an inverted top that's on there that's preventing rain. But most of them are just wide open vents. At most, I've seen some screen door kind of zip tied around it to make sure that, say, birds or squirrels don't come into that tank. We've talked quite a bit about the dust ingression, and especially say, every 100 gallons you dispense, you got to pull in 100 gallons worth of air. And we can all probably agree that dust is going to be pretty easily pulled into that. But probably one of the biggest contamination factors within fuel is actually the moisture. And we don't typically think about it from a humidity level, but let's take a look at kind of this scenario. Say you've got a humid day outside, and excuse my crude animation here, but it's humid outside, especially at summertime, depending on where you're at, that can be really sticky. We dispense, say, 100 gallons, 1,000 gallons of fuel into something. We've got to pull 1,000 gallons of volume of air back into that tank. So now we have that moisture in that headspace of the tank, which is typically fine and dandy. But as we all know, temperature doesn't stay the same from daytime to nighttime, and especially with that tank and sun beating down on it, and as soon as that sun goes away, that temperature drops dramatically. And when that does occur, we end up with that moisture now down. It condenses much in the same way that if you take a can of soda out of the fridge, it'll start to sweat. Or if you have dew on your grass in the morning or dew on your windshield of your car, that same event is actually happening inside of that tank. And when you have moisture within that tank, that creates that reg layer in the bottom. And that, especially with today's fuel of ultra-low sulfur diesel, with fuels with bio content in it, we get a reg layer, we get microbial growth, we get all sorts of things that can occur inside of that tank that really wreak havoc and cause all sorts of issues on the piece of equipment in themselves that usually rear their head as far as rapid plugging on the engine. There are solutions to this, using a breather that is going to protect both against moisture as well as particulate removal, like the one you see here. This one actually works by any moist air gets trapped on a membrane on the outside. That air comes through, then actually a particulate breather and enters into that tank dry. As that tank exhales, it pushes that moisture back off and allows that filter to be regenerative, but make sure that any of that air that's coming into that tank is clean and dry. Because if we don't, those moisture and those dirt contamination start to develop into some really, really bad scenarios. If anybody here has ever had to pay for a tank cleaning or had the habitual issue where they've got microbial growth and they're continually shocking that tank, but they can't stay ahead of it, it's because there's water in that tank. And until you actually remove that water, you'll end up dealing with issues like these, where you've got sludge at the bottom of that tank. And as soon as it gets to the pickup of where that pump is, those contaminants will be dispensed into that equipment. And then finally, last but definitely not least, and probably the most important portion of this equation, is the polish side. We want to make sure that whatever fuel we dispense, regardless if there's dirt in the tank, regardless if we've got an offloaded bad fuel, that anything getting dispensed to the equipment is going to be clean and dry and ready to use. So whether we've got a fuel sample like this, which is actually a real sample from somebody that was buying fuel seconds in Southern California from across the border, or whether we've got a glycerin dropout for some biodiesel application, doesn't matter the type of contaminant that's upstream. Once we pass it through these high efficiency filters, we can guarantee that in a single pass, we're going to meet that ISO cleanliness code that we talked about at the beginning. So it takes the guesswork out of having to test that fuel, make sure that goes off to the lab, doing patch tests, whatever it may be. These are guaranteed in a single pass. High efficiency filtration will get you to your target results. Now, one of the other questions I get quite often is, well, I already have filtration on whatever tank it is, or there's filtration that's set up on here. And what's the difference between what you're talking about and what we've been using in the past? And the big difference really comes down to the efficiency. Most filters that are out there on units today, whether it's the filter that's at a retail gas station, or if it's the filter on your typical dispensing application, whether, I don't care if they're bags or spin-on cans, most of them are somewhere around 10 to 30 microns nominal filtration. If you're unfamiliar with some of those terms, nominal filtration means average, or roughly 50%. So if we had 1 million particles down upstream of this filter, you're still going to have about 500,000 of those particles downstream. And remember, there's roughly about 1 million particles in every little 100 milliliter sample bottle. The filtration that I'm talking about is high efficiency filtration. So for example, these filters here are rated at beta 2000 or 99.95% efficiency at 4 microns. If you recall, that's that level. In between 2 and 5 microns are the particles that can cause damages to that fuel system. So for that same 1 million particles that are upstream, at 99.95% efficiency, we're only going to have 500 particles left downstream. And that's a big difference between your typical dispensing filter that's out there. Now, if you're a lot like me and don't think in milliliters and particles and efficiencies, but can probably envision what a gallon of fuel looks like, this to me helps out quite a bit. So your typical dispensing filters like you see there in the upper left, the white cans, those are going to be your 10 micron nominal filters. Downstream of that filter, you're roughly going to have about 14 million particles per gallon. Now, you do have your onboard engine filter. Those are typically somewhere around 99 or 99.9% efficient. That still means you have about 14,000 particles per gallon that make their way to that injector. Now, on the other side, if we're able to use high efficiency filtration at that same outlet, we're now sitting right at around 300,000 particles per gallon of fuel. We go through that same onboard engine filter, and now we're only dispensing about 300 particles per gallon to that injector. And that's where that big difference in the amount of life that comes from. If you remember back to that table of that injector showing how fast or slowly, depending on how you think about it, that injector life might last, it really comes down to the amount of particles per gallon of fuel that gets dispensed to that. And that's where your length comes from. So what does that mean in terms of dollars or real world scenarios? So this is an application we worked on, and they were getting right around 8,000 hour injector pump intervals from their engine application. That cost is about $40,000 all said and done before that would be revamped and that engine could go back into service. We were able to change from their current nominal filtration level on their bulk and put them in a higher efficiency bulk filtration application. So we're doing most of that work at that bulk tank. We're delivering clean and dry fuel to those pieces of equipment and allowing those onboard filters to work the way that they're supposed to. We still have that $40,000 cost to replace injectors when that needs to happen, but they were able to double the life of that injector and increase that service interval. So what you see here is kind of each one of these humps is actually a service interval where that injector needed to be replaced. Yes, we have some initial cost to be able to get that set up, and it's a change in the mindset of how we filter fuel at a bulk tank. But the return on investment here, they kept their assets for around 5 years or so, but this is per engine, right? And over the course of that time frame, we have about $150,000 in cost savings based on 16-hour day output workers. Across the fleet, that adds up to a ton of money that can be saved by just changing and spending a little bit differently and focusing your efforts at that bulk tank instead of just on the engine themselves. So overall, what are the benefits of the clean and dry fuel? We touched on most of these. We can reduce our maintenance costs. One, the premature injector and pump failure or shorter onboard filter life. If you're seeing rapid plugging of that onboard engine filter, can't get to the actual service interval that you would like there, that's most likely coming from a bulk fuel issue. If we have downtime, we all have scheduled downtime for maintenance and repairs, but it's that unscheduled downtime that kills us. You can maintain fuel efficiency. So this is kind of a unique thing to think about, but your fuel pump on those engines are driven by a gear that's right off the crank. And that crank needs to burn fuel in order to turn that pump to pull more fuel in. If we continually load that onboard fuel filter with contaminant, it's like sucking through a straw. If you pinch that down, you've got to work harder to pull that same amount of fuel through. So you end up having to burn more fuel to pull more fuel through a plugged or plugging filter that's on the engine. If we can remove most of those contaminants at the bulk tank, we actually see an increase in fuel efficiency by about 1 to 3%. And protect your investment. Remember, once that fuel is delivered to you and it's in your tank, it's yours, you own it. It's in your best interest to protect that and make sure that it's not being contaminated by any of those moisture or dirt particles that are outside of that tank being ingressed in. And then prevent that damage to infrastructure, especially if you own your own tanks. Allowing that fuel load after fuel load and that cup of dirt per fuel load to sit there and settle in the bottom of that tank, combined with water, is going to actually degrade the inside of that tank. I don't know if anybody's ever experienced or had to deal with rust developing inside of a tank or slag and actually having to replace that. A lot of those things can be avoided if we were just pulling those contaminants out before they got offloaded. With that, I'd like to open it up to any questions that anybody has regarding today's webinar.
Thank you, Matt. And just as a reminder, you can type your questions into the chat. And Matt, I have a couple to start with.
Yes.
The first one is, how long can fuel be held in storage?
That is a great question. If you've been around long enough, you probably remember fuel being able to be held, especially diesel, for sometimes years at a time. The unfortunate part is today, that's really not the case. When we reduce the amount of sulfur, we reduce some of those inhibitors that prevent the fuel from oxidizing. And realistically, 6 months is kind of your best bet, as long as you keep that fuel cool and you keep that fuel dry. If we warm up that fuel, it wants to oxidize fast. And if we have any water in there, it also wants to oxidize very fast. So typically 6, maybe 9 months if you're lucky, but the best case for it is kind of that old mantra, stored in a cool, dry place.
All right. The next question I have is, why do we have issues with microbials and algae when we didn't before?
It's another really good question. And it actually also ties back to some of those same sulfur and portions. So when we remove sulfur, that process also removes some of those inhibitors from allowing growth to occur. But the number one main reason is the biodiesel within fuel. So when we remove sulfur, that process actually removes a fair amount of lubricity for the fuel. Biodiesel is a wonderful fuel lubricity additive, but it does come with its own set of challenges. That challenge is that it is very attractive to water. And once you get water in that reg layer, microbial growth starts to occur, and it feeds actually on the fuel itself. It eats the hydrocarbon chains, and you start to develop that issue. There's one or two things. If you are able to source fuel with 0% biodiesel whatsoever in it, you typically won't get that microbial or what's sometimes called algae in that tank. Or if you are able to make sure that that fuel is completely dry, that microbial growth needs the water in order to survive. And it cannot do that without water. So as long as we have dry fuel inside of that tank, microbial or, again, algae issues disappear and will not occur again.
All right. The next question I have is, do you have an estimate of the number of customers using the bulk fuel Donaldson system here in the U.S.?
That is a great question, and probably not one that I'm equipped to be able to answer. What I can say is typically the larger the operation, the more focus there is on controlling that contamination that goes to the equipment. The other thing I can say is, about 7-8 years ago when I started doing this, the question I would typically ask is, what percentage of your fleet is high pressure common rail or 2007 and newer? And it was 30, 40, 50%, and with a lot of holdouts of, we're not buying any of that. And the last few years, as I asked that same question, the majority of fleets are all converted over to high pressure common rail applications. And there might be, a small percentage of their equipment is still some older stuff. But it's really become a focal point here, especially in the last few years, as fleets have turned over. Most everything's high pressure common rail, and those issues rear their head as either filter plugging issues or injector related problems or fuel pump related problems.
All right, the next question is, for the distributors that are on this webinar, who are the potential customers for this product?
Another good question. Probably some of the similar things of what I just answered in the last one is that asking that type of equipment, right? Anything that is high pressure common rail, kind of the cutoff you can use as a hard stop date is 2007 and newer, is almost all going to be essentially high pressure common rail. But it's also anybody that has their own fuel tank, right? Somebody that's got fuel on site, somebody the higher volume of fuel, probably the more interested that they're going to be in that and protecting that, the higher volume that they're burning through. But, fleets or refuse, it's a really wide range for that, for this type of high efficiency fuel filtration.
All right, the next question is, does filtering the fuel remove fuel additives?
Does filtering the fuel remove fuel additives?
Yes.
Is that the question? Yes.
Yes.
No. There are some times where fuel additives can cause some rapid fuel plugging. In short, without going into a really deep tangent, fuel additives is kind of like playing with the chemistry of the fuel. I grew up, personally, there's probably a lot of people on here that are the same way of more is always better. If, a ratio of 1 ounce to a gallon is good, man, throwing the whole bottle in there is probably going to be even better. The unfortunate thing is you can actually oversaturate with additives, and then you get a bunch of dropout that happens. And kind of like if you take salt, you can dissolve it in water, but at some point that salt drops out. You're going to have salt laying in the bottom of the glass. That same thing can happen with additives. So while properly dosed and mixed correctly in the right ratios, no, their filtration will not pull it out. It is able to be dissolved in there, and it doesn't pull it out. Where you do sometimes see that is when overdosing happens, or we're dosing at the wrong time within the equation, you can get chemical dropout. And essentially at that point, any filter is going to start to pull that stuff out, regardless if it's a high efficient filter or even those nominal filters we were talking about.
All right. And the next question, is there any data relating to decreased miles per gallon or increased fuel burn per hour?
I'm not sure I understand the question. Is there any data related to, say that again?
I assume that they're talking about when the fuel injectors are damaged. Is there any data relating to decreased?
Sure. I got you. Yes, absolutely. And to be all honest with you, a simple Google search will bring you up about probably a dozen different white papers discussing that. And that's not a new concept, even with high pressure common rail. Even and probably you can think of even in your own personal vehicle, if you start to have injectors that are not spraying correctly, you'll start to see decreases in fuel mileage. And that really comes down to the atomization of the fuel. A nice fine mist gives you a lot of surface area on each one of those little droplets of fuel, so it can be burned correctly. It's the same way that, if you don't have that, or why you can't really run an engine by just kind of pouring gas down the intake, it needs to be atomized. It needs to have that right ratio of fuel to air. And when you don't atomize that fuel correctly, that injector starts to become, let's call it weak, but essentially that nozzle is more open. You're not going to get that correct burn, and you keep having to burn more fuel in order to keep that engine running. And yes, you will see a significant decrease in mileage and or efficiency.
Great. The next question is, does Donaldson have live fuel monitoring systems with data logging for warranty purposes or preventive warning alarms?
Great question. We do have a team here that is our FilterMinder Connect team that works with data logging and being able to put sensors within a circuit to monitor a whole slew of different things, not just fuel, but they do a broad range from air, lube, fuel, and into the hydraulic space as well. So if there's any inquiries about that, I'll be honest with you, I am not an expert of talking about that, but I know we're able to do some really unique things with data monitoring, logging events, and being able to see what is specifically going on within a system, and specifically how it relates to the filtration side of it as well. But absolutely, if there's any questions or interest in that side of it, please reach out to your Donaldson territory manager. We can get you guys in touch with the right folks here that can talk on that topic a heck of a lot better than I can.
And if you're not sure who your Donaldson territory manager is, after this webinar, you'll be receiving an email with an opportunity to request more information. Matt, you talked about diesel engines after 2007, which would be for the on-road. What about off-road? What are some things to listen for?
Great question. So the terms, both on-road and off-road, so like Lori mentioned, on-road usually is deemed by EPA 2007 and newer. For off-road, which I assume is probably a lot of folks on this call, it's Tier 4 applications. But realistically, for off-road, it started being high-pressure common rail back when you started seeing Tier 2 engines. But I kind of use that 2007 as a cutoff point. Whether it's on-road or off-road, that is essentially kind of the hard stop where non-high pressure common rail engines were able to be used because they didn't meet the EPA standards that were set. So yeah, there's a set of rules for on-road, there's a set of rules for off-road. In today's environment, those set of rules are the same. We called them two different things for a while because there was different loopholes for on-road and off-road. But you can be assured that essentially Equipment 2007 post is going to be that high pressure common rail type environment. You will see it before. It's just there's not it's harder to say for certain which engines did, which engines didn't.
The next question is, what's the average lifetime to change the filters? And I assume that would cover when you're first applying a bulk filtration system to a dirty tank versus maintenance, and how often you change filters in maintenance.
Yeah, great question. So I'll answer it this way in kind of two steps. Kind of going back to some of those images I showed of your typical cellulose filter that's on there, that's kind of a nominal rating. Most of those that you saw there were very sun faded. They might have rust on the can. They look like they've been there for a really long time. They are on there for a really long time, and they last a long time because they're not really pulling much out of that system, right? You can have really dirty fuel, but you're not actually removing much of it with those elements. A high efficiency filter on the bulk tank is going to need to be replaced. It isn't something that's going to last you 3 years that's sitting on there, but they are typically designed with a mindset of being able to get high flow rates as well as long life. And what I kind of use as a rule of thumb, and this might be getting into the weeds a little bit, but for each one of those cans, if the upstream cleanliness is around a 19, you should be able to get somewhere, give or take, 80,000 gallons out of it. Now, the caveat with that is if you're at a 20 in that tank or a 21, each time you go up a code, you're going to half that length of that element because you're going to double the amount of dirt that's upstream, right? So it can get very short very fast. What I typically tell folks as a rule of thumb, if you know you have a contaminated fuel tank and you know you have issues, it's probably in your best interest to clean that tank before implementing outlet filtration. You can do it the other way around. You can put outlet filtration on. If you have a really dirty tank, you're going to go through filters pretty fast at the beginning. Depends on what that volume of fuel tank, essentially you'll kind of half-life it every time through, and eventually you will get it cleaned up going that route. But it could be more cost effective to actually clean that tank. Best case scenario would be clean that tank before implementing it, but I understand the real world that that's not always going to happen. So you may take, at your first installation, might have some more or a higher frequency of those element replacements as that tank starts to kind of clean and sort itself out.
All right, the next question. We experienced premature filter changeouts on our Donaldson DBB range due to low pump pressures below 45 psi, and then in colder conditions when winter waxing occurs in diesel. How do we prevent irregular filter changeouts due to these key factors?
Sure, good questions. I'll give really high-level answers here because the detailed answer probably deserves its own 30-minute plus webinar. But in short, pumps are a big part of it. So if you're going to talk in your average red fill right pump, those have an internal bypass, typically somewhere like 15-ish PSI. That bypass valve will open on the pump before actually that filter gets to its useful end life. That filter, the typical high efficiency filters they can go up to about 150 PSI before you would actually see a structural change in that filter. So there's a lot of runway left on there, but it's actually the pump that can't keep taking that head pressure that you're putting in front of it. So that can be handled by one of two ways. You can add more filters in parallel to keep that pressure drop down, or you can modify or change that pump to increase that relief valve within the pump to be able to overcome the restriction that you put in front of it with filters. To the second part of it, as far as waxing and concerns like that go, that is true. I mean, so if you're running a number 2 fuel, you're going to get waxing depending on kind of where you're at. Somewhere probably, could be 30 degrees, 40 degrees, could be lower than that. That isn't a point that's well regulated, and it changes all over the region. But we do have a filter element that is the winter filter element that is specifically designed, or there are filter elements out there that are specifically designed for winter to allow those wax particles to make their way through. You're going to, unfortunately, sacrifice a little bit of fuel cleanliness during that time. Kind of the line I draw is anything north of St. Louis, you should be using some type of winter element, between October to April. You may have to use some south of that, but as a rule of thumb, anything north of St. Louis should kind of be in that realm. There's all sorts of different additives you can do to try to change, augment, prevent that waxing to occur. That kind of goes back to making sure that those are dosed properly. That's, without getting into it real deep, it's kind of the quick, short answer for it. If you do have some more questions on that, feel free to reach out to us. We're more than happy to run through and explain some of those in greater detail and maybe help sort out an issue or problem you might be seeing.
All right, the next question is, do you suggest to put the 7 micron on the inlet and 4 micron on the outlet here in the U.S.? And it's to make the balance. Oh, sorry, it's to make the balance between the filter cost and the fuel quality.
Yeah, good question. That's typically best practice. So if you're not familiar, and I call there's a filter that is the 7 micron high efficiency filter, and then there's the 4 micron high efficiency filter we've kind of been talking about throughout this. Typically, the more open filter gets used on the inlet and the tighter one on the outlet. You could run them both at the same level, the 4 on the in and the 4 on the out. The only thing that you'll probably see is higher filtration element replacements on the inlet side. The 7 will get you to a target of about a 16. So you've cleaned it up dramatically. You are allowing a little bit of dirt in, but you're going to catch it and polish it on the way out. So that is best practice for that. But again, you could do it both for in and out. The only thing you'd see is probably higher change outs on the inlet and probably a reduction of change outs on the outlet. Good question.
Matt, how often should bulk fuel tanks be cleaned?
That is a wonderful question. So if you are filtering at the inlet and you have good breathers on there and not allowing contaminants to make it back into their tank, realistically, you can kind of go indefinitely without tank cleaning. If you are running wide open vents and not doing any inlet filtration, on average, for what I see, say like on a 10,000 gallon tank that gets filled, say once a week or once every other week, those types of, and it also depends on the environment, but those scenarios usually are forced to clean their tanks about every 3 years. That's because that dirt and a reg layer gets to a point where it's at the pump pickup and they're forced to deal with it. A lot of companies that run wide open stuff will do annual cleanings to stay on top of it before that ends up hitting the reg layer. But essentially, if you do inlet filtration, put breathers on there, you're essentially sealing off that tank from the outside world. That expense of having to clean tanks is essentially negated and doesn't have to occur anymore because you're not allowing that contaminant back into the tank.
So Matt, it's now 11:56. I think we should take this last few minutes to wrap up the webinar. There are a few questions that we didn't get to. You're going to be receiving a follow-up email. I highly encourage that you reach out and ask any questions that didn't get answered during this webinar. Next slide, please, Matt. And for those of you that would like a certificate of completion, Please look to that email to request that certificate of completion if you want to use it to potentially fulfill your CE credits. And with that, I would like to thank everyone very much for attending today. And if you have questions, please let us know and contact your local territory manager for support, or go to our website and you can contact us from there. Have a great day.